Okay, so how are we all doing today? Good. How was the first time I've seen you since assignment 7 was due? How was that? Easy? Hard? Not too bad? Learning experience? Um, and some of you had a tutorial today, right? Yeah. How did that go? Anybody demo any games? Okay. Um, so the woman who organizes the tutorials and the grading of your assignments has offered to coordinate demos of your games in a couple of weeks or so, or maybe a week or two, where basically during a tutorial you can you can come up and give a 5-minute demonstration of the game that you made, showing some of the levels. It would be done on the projector so everybody gets to watch it. If you're not comfortable standing up and talking to people about it, you can tell her that, and she can demo the game for you if you don't like public speaking. So my question, I have 2 questions for you. So one is, how many of you might possibly, if your game works out well, be interested in having your game showcased this way to the other people in the class? Okay, so a handful. How many of you would be interested in seeing other people's games showcased this way? Yeah, so notice the problem with that is there's a lot more people who want to see games than there are who want to show off their own. I'm told that the typical thing that happens in these situations is only a handful of people volunteer, but after seeing what the volunteers produced, people who are in the audience say, hey, my game was as good as those, and they get up and show off their game too. So look forward to that maybe in a couple of weeks. It'll be probably well after the assignment is due and hopefully marked, so that if there were some little bugs still in your game, you can iron them out and have them corrected before demo day. Okay. Last class, we got everybody up to speed on recursion. Did anybody have any questions for me about any of that stuff? It was fairly clear. So we talked about recursive functions, how they need base cases in order to stop them, how they somehow need to make something smaller so that you're always getting closer and closer to a base case so the thing eventually stops. So sometimes it's the length of the array that's getting smaller, or the argument n that's getting smaller. And if your recursive functions are too deeply recursive, then what happens is the recursion stack blows up and you get a stack exception or a runtime exception complaining about a stack overflow. And we even saw a sort of fancy trick where writing a recursive function that added up an array by summing the elements one at a time caused stack overflows as soon as the array was of length bigger than 1,000, but one that did a more nicely balanced way of doing it, where it added up the first half and then it added up the second half, it could seem to handle arbitrarily large arrays. So we're good to go, and hopefully we all understand that. So now we're really ready to study algorithms, including recursive algorithms, and some of the ways of analyzing them. But before that, we sort of need to understand how much things cost. So generally when we're studying algorithms, the point is to make fast algorithms. And so if we want to talk about fast algorithms, that means we need to know what sorts of things are slow and what sorts of things are fast. And this is something that, was so long ago for me, I take it for granted that everyone knows this, but it's not necessarily the case. So there's a cute little function in Python there's a module called timeIt, and in there there's a function called timeIt. So what does timeIt do? It takes a string as an argument, and that string is a piece of code. And it runs that piece of code 1,000,000 times and reports how long it took to execute that code 1,000,000 times in seconds as a float. So there's a piece of code, x equals 2 plus 2. It's a piece of Python code, and it can execute that 1,000,000 times in 4/100ths of a second. So if we extrapolate, that probably means it could do it 20 million times per second, this piece of code. So not a complicated piece of code, and it's very fast. So this, if we're going to talk about fast versus slow, we want to know these kinds of things. And it's not too surprising that this is a fast piece of code. What happens in that code? Well, two numbers, two constants get added together, and they get assigned to a variable. Nothing big. And these are somehow all fundamental basic operations that happen in computers. So adding two numbers together, two integers together, assigning that result to a variable, these should all be things that computers do using a handful of instructions. So you know that computer speeds are measured in gigahertz, so what does that mean? Well, gigahertz is hertz is a measure of cycles per second. Gigahertz is billions of cycles per second. And instructions that take place in a machine usually take a few cycles to execute. In Python, they take probably a few hundred cycles to execute. But since this thing has a processor speed in the billions of instructions per second, it's still able to execute tens of millions of Python instructions per second. Okay. So there's something really fast, adding two numbers together. We could try, I'll demonstrate a little bit more of this timeIt functionality. So you can give it one argument, and that argument has to be a standalone piece of code. It can't rely on anything else. It can't rely on any global variables or anything. So I can't say, for example, a equals 23, and then time the code x equals 2 times a. I'll get an error that says this global variable a is not defined. So this piece of code really is basically firing up a whole new Python environment just to run this code 1,000,000 times. Now, if you need to do something like this, timeIt takes a second optional argument which sets up any, you can set up anything that you need. So what happens when you call timeIt this way is exactly once, this piece of code gets executed. So this defines a variable a that's assigned the value 345. Then a timer starts, and then this piece of code gets executed 1,000,000 times. The timer stops and reports how long that took. Okay, so this doesn't count in the time. It's only executed once. This gets executed 1,000,000 times, and it's whatever it lives in whatever is left over after this first part was done. Okay, so there that increases the time a little bit. Now, because we're doing multiplication and we're not, it's not just of constants, but there's this variable a that has to get looked up. But still, it's about 1/10 of a second, so that means it could do this about 10 million times per second. And you have to remember that right now this thing is sharing CPU and memory latency with this video recorder that's running as well. So if I turn this off, it would probably be faster. Okay, so there's a very sort of basic thing. And all of the standard arithmetic operations are fast like this. You know, A times B, A plus B, plus is faster than times, A divided by B. Yep.
Why can't we time it?
Why can't you time it?
Yeah, like see how many times it takes to run time it 1,000,000 times.
You can.
I tried.
Did you import time it in your header code? Let's see. Import from time it. Import time it. So then I would run time it.
Never mind.
It works. So it seems to be doable. But time it internally is running this code 1,000,000 times, and this external one is going to run that 1,000,000 times. So we're running it a lot of times. So you can do it, but you're going to be waiting a while. Right. So we saw that the internal one works in something like 1/10 of a second. So then the total is going to take about 1,000,000 times 1/10 of a second, which is still a lot of seconds. Yep.
Do you mind wiggling your board around to fix the screen there?
Oh, wow, cool. It's on the end, it's on this end, which is bad news because this is the thing we have to use all the time. Okay. All right, so these basic operations, time it, not included, but addition, subtraction, multiplication, division, mod operations, some of them take a little bit longer than others, but nothing serious. So all of these things take a handful of CPU cycles to execute, so they can execute millions of times per second. And you know, the more complicated your expressions are, sort of the longer that they'll take. Plus, you know, takes a little bit longer, but it's sort of as you'd expect. The bigger the expression gets, the longer it takes, but it's only in time proportional to the number of operations you're doing inside that expression. So we went from an expression that did one arithmetic operation to one that does 1, 2, 3, 4, 5, 6, and so the time blew up by a factor of, I don't know, close to 6 in this case. And if you use floats, then that takes a little bit longer than integers. So here, if we switch A and B to be floats than integers, then the times go up. So maybe it takes twice as long to do floating point operations as integer operations. The one thing to look out for that you have to be careful with in Python, and not so much in other languages, is there is one operator which can take a long time, and that's exponentiation. And that's because, well, let's say 2 to the A. That can take quite a while, and well, quite a bit longer. So if A is 345, it's that, but if A is, let's say, 1,000, now we're not talking about times in, you know, less than a second, but they're getting bigger, and somehow the bigger I make the exponent A, the longer it takes. So it took for the exponent being 1,000, took 7.5 seconds. Now I'm expecting something around 15 seconds. We'll see. '18 seconds. And Well, that's just because exponentiation can easily produce results that are bigger than your basic little int, right? Remember, there's these two kinds of integers. There's the usual kind, and once those get too big, you switch to this long kind of integers that when you print them in raw format, they're suffixed with an L to tell you that this is a long integer. And operations on long integers take time that's as long as the integer, basically. So, you know, this is an integer with about 600 digits, so so it's going to take about 600 times as long to do operations on this as it does to do on regular small ints. Yeah.
Why did it take you 18 seconds to do the timing? It took you less than a second to print.
Because time it executes this code 1 million times. I only executed it once here, so so it should have only taken me about 18 seconds divided by 1,000,000 to execute that. Probably took longer to print it than to calculate it, in fact. Okay, so that's great. If you don't feel like entering Python's interactive mode, you can also do it from the command line. Looks like this: Python -m time it. You specify the setup code as the first argument, and you specify the code to execute as the second argument. So this will set x to 2, y to 3, and then it'll repeatedly compute x divided by y, and it gives slightly more informative output. So it ran it 3 times, and it shows you the best of the 3 results. That makes sense for what that makes sense because the best somehow should be representative as the best your computer can do if no other task comes along and tries to interrupt in the middle of the process. And then it tells you, you know, this was the best one that it could do. Okay. All right. So basic arithmetic operations, comparisons, exponentiation if the exponent is not too big on either ints or floats, they're all very fast. And we'll say that they take constant time, meaning that, you know, they take a handful of computer cycles. Other things that are fast, or other things we can check, lists were something that could potentially be slow, right? They get big, so there could be issues. So we could look, for example, what does it cost to look up a value in a list? So to look at the ith element in a list, and so there we'll set up a list. A is a list of length 10, and maybe I is equal to length of A divided by 2. Okay. So what does it cost to look at the middle element in a list? How expensive is that? So in a list of length 10, it's very fast. How about in a list of length 1,000? Is this going to be faster or slower? No difference. So is it going to be faster? It seems unlikely, right? It seems unlikely that we give it a bigger list and it's going to be faster. The question is it going to be slower or not? And the answer is not. And it doesn't matter if the list is of length 1,000 or even if the list is of length 1,000,000, it still takes just the same amount of time to access an element in that list. So, you know, in the list of length 1,000, I can access the 500th element in, you know, whatever this is divided by 1,000,000, and in a list of 1,000,000 I can access the 500,000th element in the same amount of time. Doesn't cost anything. It's not really expensive to access elements in a list given their index. And similarly, it doesn't cost much to set the elements of a list. So changing the value of an element doesn't matter how long the list is. And that's because internally Python lists are stored as arrays. That's why I just keep mixing up the names, lists and arrays. Basically, they're just stored as a whole bunch of a whole chunk of memory that's all consecutive. And when I want to access the element at position I in the array, all I do is I start at the beginning, I add I to that address at the beginning, and I go to that place in memory. So all it is just looking something up in memory after doing one addition, which is adding the index to the base, the starting location of this array. So arrays are fast for changing, modifying things or looking things up given their index. Something else we can check. Calling a function. Is that fast or slow? Or does it take a long time? Well, let's see. So we'll need to define this function foo. So here we define a function foo of x. All it does is return 2 times x, and then we call it 1,000,000 times. We'll see how long that takes. We have to call not foo of x, but foo with some argument, I don't know, 45. So it's a little bit slower than the basic arithmetic. For example, it's slower to do that than just do 2 times x, whatever. That's a little bit slower than, so it costs something to call a function. And we shouldn't be too surprised by that. That's because calling a function requires creating this stack frame, setting up this variable x in the stack frame. When the function is finished, it has to return the value and remove the stack frame. So that takes a little time, but it's not out of this world. So, we go from something that takes 8/100ths of a second to something that takes a quarter of a second. So it's maybe 4 times slower than just the act of multiplication that takes place in this thing. So calling a function, just the act of calling it is not terribly expensive. If the function does some very slow stuff inside of it, then that'll be slow, but just the calling overhead is not much. And the other thing that we've looked at and that you've used before are sets. So let's try doing something with a set. So here I'll create a new set that contains the integers 0 through 10, or 0 through 9. And what are the operations that we do on sets? What are sets good for? Yeah. Checking if something is in a set. So let's check if some value is in the set. So S is some set, contains 0 through 9, and let's say the value we're going to search for, just for testing purposes, is ln of S divided by 2. So it'll be 5 every time. So that's fast. Checking if something is in that set is fast. Now, this is just a set with 10 elements. What if I make it bigger? So what if I put 1,000 elements in that set, or even 10,000 elements? Is that going to be faster or slower? Yeah. Should be the same. So sets are implemented using hashing. Hashing is a trick that basically turns a problem of looking in a giant set into one of looking into a small list. And so if we do this, yeah, there's a little slowdown, but not a ton, right? I mean, we went from 8/100ths or 10/100ths of a second to 14 or 15, but the size of the thing increased by a factor of 1,000. So we cannot have sets of lists because lists are not hashable. So Python doesn't want you putting lists in sets, and the reason for that is that you can change lists, and that's not changing stuff that's inside a set is not a good idea. If you want to do something like that, use tuples instead. So you can convert your list to a tuple. The thing that's special about tuples is they're almost exactly the same as lists, except you're not allowed to change the values stored in a tuple. And Python is happy to store tuples in sets. Okay, so it doesn't matter if this thing has 10,000 elements or 100,000 elements or even a million elements, or we'll see if 10 million will fly. Yeah, even 10 million elements doesn't take any longer. In fact, you'll notice that there's a longer delay now, but the part that's taking longer is the part where we actually make the set, because we have to cram 10 million elements into the set. Once we get to this stage where we start timing how long it takes, it doesn't take any longer than if there were 1,000 elements or even 10 elements in the set. Okay. And we can, the other two operations that sets do well are removing and adding. So now we can repeatedly remove and add an item X just to see how long that takes. We do this a million times, it takes half a second to do it, and it's not really going to get much faster if the size of the set decreases. Down from 1,000,000 to 100 makes no difference. Okay. So that's really really important property of sets, the thing that makes them really useful. It's why in assignment 5 or 6 you're asked to use sets to do things. It's why in the midterm exam there was a question that showed two ways of computing anonyms. One way takes forever and the other way is super fast. It's because they're using sets. Now, at the other end of the spectrum is when we don't use a set. Instead, we just use a list. So now S is just a list of 10 elements. And, checking if X is in the list, not bad. 0.2 seconds to do it 1,000,000 times. But now, increase the size of the list by a factor of 10, and it takes not quite 10 times as long, but getting close. Increase it by a factor of 10 again, and now I expect we're going to wait about 14 seconds for this to finish. And that's because this line of code here, X in S, the way that's implemented when S is a list is to start at the beginning of the list and walk through it one element at a time until you reach the value, till you find the value X that you're looking for, or you get to the end of the list and you don't find it. So looking things up by value in a list is very slow. Getting the element at a particular index is fast, but asking if something is in a list, that's a really slow operation. The slowest is when it's not even in the list at all. Then it'll actually take about twice as long as this did, because this only had to look halfway through the list to find it. Now it's going to have to look through the entire list to realize that it's not there. Okay, so while we wait for that to finish, any questions so far? Okay. So Oh. Well, it's about what we've learned. So things that are fast. So fast operations. And fast here means constant time that have nothing to do with any variable values. So we've got basic arithmetic and comparisons on integers and floats. And on integers, I should specify that it's only on those short ones. If you work your way up to long integers, then that can get slow. Calling a function, that's fast. Accessing or modifying a list value, so that's this A at I kind of thing. Adding, removing, or testing if a value is in a set. And we won't test it, but accessing a dictionary by its key, that's also fast. So yeah, that took 56 seconds to determine that this thing is not in the set. So very slow. All right. So the slow operations. We have that checking if a value is in a list. So that's this operation x in A. And slow operations for right now means that they take time proportional to the size of something. So len of A matters here. So it matters if the list is of length 10 or if the list is of length 100. One is going to take 10 times longer than the other. How about so we saw that accessing a value in a list is fast. It doesn't matter how big the list is. Now, we've also seen that this list indexing operator actually has some extra things that it can do, right? It can also take slices. So it can grab out sublists. So for example, if I do this, do you think that'll be fast or slow? So it's slower, but not super slow. What would make it slow? Well, first of all, what is this code doing here? A at I to I plus 10. Yeah, so it grabs elements at positions I plus 1, I plus 2, I plus 3, all the way up to I plus 9, and makes those into its own little list containing 10 elements. So what do you think would make this code slow? What could I change here that would suddenly make it slower? Yeah. Yeah. So taking a slice of a list, it doesn't matter how big the list is that you're slicing from, but the size of the slice that you're taking, that's really important. Because basically you're going in and copying a big chunk of the list into another location. And the more you copy, the longer that that's going to take. I mean, we've already seen that accessing each individual location in a list is very fast, but once you access enough of them, that starts to add up, and that's what's happening here. So, so the time, I mean, this is optimized to be as fast as it can be, but it still doesn't totally save you. The more you try and grab, the longer and longer it's going to take. So this one is going to take something around 60 seconds to complete, and I don't feel like waiting for it. Okay, so slicing from a list takes time as well. And now, this shouldn't be a surprise, but any kind of iterating that you do takes time. So, for example, if I do something like, say, for x in A, so here's a stupid loop that says for every element x in A, do nothing, skip, pass. How long does that take to execute? Well, it depends how long A is. Because really this is like saying, this loop expands out into x equals A at 0, x equals A at 1, x equals A at 2, x equals A at 3, and so on. And one of those things means it executes 10 times, another time it executes 100, and another time it executes 1,000 times. So don't execute anything, it's still going to take time. So slicing a list, it's the size of the slice that matters. And iterating over the list, it's the length of the list that matters. Okay, so let's define a couple of functions. So we have two things to look at. So let's define foo of x as returning 2 times x plus 3. So given what we've just talked about, if you had to describe the running time of this function, how would you describe it? Yeah.
Very fast.
So this should be, I don't know, quite fast, very fast, very fast. Probably the best way to describe it is to say that it takes constant time. So it doesn't really matter as long as x is just a small, a regular integer or a floating point number. This will take some time. That's a few cycles of CPU time, but nothing crazy. Okay. So this one I would describe as taking constant time. So here's another function called bar. This computes the sum of 0 up to n minus 1. Now, if you had to describe the running time of this function, how would you describe it? Yeah.
Depends on the size of n.
So it depends on the size of n. So running time is proportional to n. And we can sort of see that because we can just look at each line of code here. We create a variable c and we set it to 0. Well, that we've done lots of times. That just takes constant time. In this line of code, we set up a for loop, and in that for loop, we create a range, which is actually an array containing n elements. So we didn't do this explicitly, but making an array that has n elements takes time that's proportional to the length of the array. So range of n takes time proportional to n. Now this line of code looks simple. It just, adds x to c. So this takes constant time, but there's something more we have to look out for here. Yep. Yeah, so this takes constant time, but gets executed n times. So it's whatever that constant is, it gets multiplied by n. So, so in total, what does this line of code contribute to the running time of the function? It's proportional to n because it gets executed n times. And this is okay. So that's how we analyze this thing. And indeed, I won't time it because it's annoying to set up. But indeed, if you time this with different values of n, you'll see that n is 100 is about 10 times longer than n is 10, and n is 1,000 is about 10 times longer than when n is 100. Okay. Now, when we start talking about the running times of algorithms, we get a little bit fed up with expressions like takes time proportional to n. We get tired of saying things like this, and we should maybe even ask ourselves what that means, takes time proportional to n. So takes time proportional to n really means that takes time c times n for some constant c that I don't feel like specifying. That's an even wordier way of saying it, but that's what time proportional to n means. It means some constant times n. That constant is probably measured in millionths or billionths of a second. And I don't feel like telling you what it is because I don't feel like figuring out how fast my processor is exactly. And we do this kind of stuff so much that we've developed a shorthand for it, or we've borrowed one from mathematics, and that's what's called big O notation. So this, when I say something like it takes O of n time, it means it. Okay, can you guys stop talking, please? If I say it takes O of n time, that means it takes some constant times n time that I don't feel like mentioning right now. So I don't feel like telling you exactly what that constant is. Okay, so that's what big O notation is. And all of these things that we write here where we say constant time and time proportional to n, we can instead use this big O notation just to shorten them up. Constant time means O of 1 time. It means some constant times 1, and I don't feel like telling you what that constant is. Time proportional to n means O of n time. some constant times n. I don't feel like telling you what that is. This takes time, constant time, but gets executed n times. That means overall it contributes time proportional to n, or O of n. And this takes constant time, which we now call O of 1. And so if you want to really look carefully at what what the running time of this function is, it's O of 1 for the first line plus O of n for the second line plus O of n for this, plus another O of 1. And whenever we have this kind of complicated sum of all these big O's, we cheat a little bit and we just keep the biggest one. So n usually is bigger than 1, so we'll just keep O of n as the description of this thing. Okay. So this function takes O of n time. All right. So far, so good? So in another class, you will learn a formal definition of this big O notation. But right now, you don't have enough you don't have enough background to understand the formal definition yet because it involves sets. But we'll just use it in a sort of sloppy way where we'll wave our hands and say, oh yeah, it looks like O of n, O of 1, and so on. And when you add up a bunch of these things together, you just keep the biggest one. Let's try another one. Computes. Yeah, so really when I use big O like this, I'm actually only telling you that it takes at most constant times n time. It doesn't mean that it has to take that length of time. And it's useful because that's usually what you're worried about. What's the worst thing that could happen? So similar looking code. So it's almost the same code as above. So what's the running time going to look like? Yep. So the suggestion is that it's proportional to n. Well, let's analyze it one line at a time and see. So this line here, I'll stipulate that it takes constant time, O of 1. That's just assigning a value here. This line here, this creates a range containing n values, and that takes O of n time. Now this line here calls bar of n. How long does it take to run bar of n? Well, we did that calculation. It's up here. It takes O of n time. But this line of code gets executed n times. So actually, its total contribution to the running time is n times O of n, which we write as O of n squared. Or if you like, n times n, so there's no confusion. Okay? And this takes constant time. So in total, we're getting O of 1 plus O of n plus O of n times n plus O of 1. Now, when you add up big O notation things, you just keep the biggest one, which one of those terms is the biggest? O of n times n, right? Because if n is 100, well, n is 100 is bigger than 1, so that doesn't work. But n times n is then 10,000 if n is 100. So really, O of n times n is the biggest thing. So the running time of this function is O of n times n, or we usually say O of n squared. Okay. So let's see if any of this has anything to do with reality. All right, so we defined foo, which was supposed to be super fast. So foo of 10 takes no time to execute. Skip right to the end. Doesn't matter what kind of argument I give to foo. Takes constant time. Here it's starting to slip a bit because I'm getting to these bigger integers, but you know, this is an argument of, I don't know what it is, 100 million or something, or more. So that's not really, the value of the argument x is not really an issue when it comes to the running time of foo. Now for bar, super fast, super fast. But now we start to notice that it's taking longer and longer. And indeed, it's going to take time that's you know, proportional to this value of n, because it's iterating over a list of n integers. Okay. All right. Now foo bar, this is the one that takes n squared time. This is the biggest running time that we've seen so far. So foo bar of 10 is really fast. Of 100 is really fast. Of 1,000 is really fast. Of 10,000 takes a little while. So I don't know what that was. 10 seconds maybe? Something like 10 seconds. So if I add one more zero, so I increase the size of this thing by 10. And if it took 10 seconds before, how long is it going to take now? 100 seconds? So that's the guess. Well, let's run it. and instructions versus something that takes 10 billion instructions, basically. So big difference. Okay. So any questions about that? All right. So next I want to have us develop a fast algorithm for a problem that actually you already know the algorithm and you know how to solve it, because it's something we did on the third class, maybe the fourth class that we had. And the problem is the following. I give you a sorted array. So the elements in the array are sorted in increasing order, or at least non-decreasing order. And I ask you to tell me whether or not X is in the array. So if the array was unsorted, you know, we could do something like this, return X in A, but we know that that's going to be painfully slow because, well, that's going to take time, order the length of the array, and so we want to do better than that. We want to use the fact that this thing is sorted. So determine if X is in the sorted array A. And we'll say, because we like this O notation so much, and we like the variable n so much, we're going to do something that every algorithmist does, which is to define n as the length of A. So in any analysis that we do, we'll define n to be the length of A. And so in a statement like this takes O of n time to execute. Right? We saw that if I just use the built-in check to see if X is in A, then it's going to go through and look at the elements of A one at a time until it finds one that's equal to X or it doesn't. And so in the worst case, it's going to go through the whole, all n elements and report false. So I want to do better than that. So what does this remind you of from our third or fourth class? Yeah. I don't want to do that because, I mean, I could do this, say S is equal to a set A, and then return X in S. Then this would take constant time, but I had to go through all the effort of converting this thing into a set, so that takes order n time. So that just shifts the work around. Instead of looking through the array to find X, I'm going through the array and putting all its elements in a set. Yeah?
We can take a random index of the array and check if the element is higher or lower than the value we're looking for. And then
Okay, so we could take a random index and, you know, A at position R, where R is chosen randomly, and check if the element we're looking for is less than or greater than that. Why random? Yeah. Yeah. So remember this guessing game, which was one of the first things we implemented. The computer guesses a number between 1 and 1,000, and it's willing to answer questions about that number of the form, you enter a number and it tells you if it's higher or lower, and you have something like 12 guesses to get it, or 10 guesses to get it. And we figured out that really, in that case, the best first guess is 500. Because no matter what the computer tells you after that, it's either going to tell you, great, you guessed correctly, that seems unlikely, or it's going to tell you it's less than or greater than, but in either case, there's only 500 elements you have to worry about. 500 answers it could be, half as many as there were before. So we can do the same thing here. So these ideas don't work, but we can say something like, let's say M is equal to the length of A divided by 2. And now we'll say if x is less than a at m, then what should we do? So intuitively, we want to recursively search a0 up to a m minus 1, right? Otherwise, if x is bigger than a at m, we want to recursively search a at m plus 1 up to a at ln of a minus 1. And then finally, if x is not less than and it's not bigger than, then it must be equal to, so we would just return true in that case. Yep.
If it's for the second one, if x is greater than a at m, if you do the slicing, for the first one, if you do the slicing, it doesn't give you m. That's, even if you include m, that's from a at 0 to a at m.
Okay, so let's let's see how we could implement this using array slicing. So we don't specify the first endpoint. That means it'll give us 0, and we say we want to go up to we want to include m minus 1. So we just use m as the argument there, and we search for x. In this case, we want a slice that starts at position m plus 1 and goes to the end, and search for x. Let's not forget our return statements. So let's try this. So a is equal to range, I don't know, 100. There's a. It's a sorted array, so it should work for binary search. So if I do binary search 55, oh yeah, binary search A 55. So true, 55 is in there. Yep, there it is. 56. Can I try what? 51. Yep, it's in there. So great, this works, right? Something fishy about this code. So give me something that's going to break this code. Give me a search that's going to break this code. Actually, really, really big numbers aren't going to break it. A letter, or letters might break it because it might say that you can't compare these two, not allowed to compare integers and letters. It's a bit cheating. But how about 51.5? 51.5 is not in there, right? It's only integers that are in there. So if I look at this code, the thing that should be bothering you is there's only one real return statement in here, and it returns true. There's no place to return false.
So if it's less than, it's just going to check again, check again, check again, check.
Let's see. No. So it actually doesn't give an infinite recursion. That's only, I don't know, 8 levels deep or something. What it actually gives you is a list index out of range error. So that's in this line right here, where it checks if x is less than a at m. So anybody want to guess what the value of m is here and what a looks like at this point? Yep.
Would maybe like 51 and 52, or maybe just 51 and then just 10 find it?
No, this shouldn't cause a problem, right? M is the length of a divided by 2, so that should be a valid index, except well, I mean, this thing is actually going through. We can print exactly what's happening here. Maybe we should just print A at each step and see where this thing breaks down. Print A. And if I do something like binary search A55, you can see what happens. We start out with the full list. Well, we start out with the full list with all 100 elements. At the next stage, we have 51 through 99. At the next stage, we have 51 through 74, 51 through 62, 51 through 56. Then we get 55 and 56, and then we get 55, and we return true. Now, what happens when we search for 55.5? Well, exactly the same thing happens. There's the printout. We started with everything, then we got 51 through 99, 51 through 74, 51 through 62, 51 through 56, 55, 56, 55, and then the empty list. So what we do here is, so the length of A is 0, we divide by 2, we get 0, and then we ask for the 0th element of an empty list. And that's the only time that this thing could give us an error, is if there's nothing there, right? Yep. Well, at some point we have to return true. So there has to be somewhere we return true and somewhere we return false. So. Nope. And let's. That's true. 55.5 is false. 99 is true. 100 is false. 1000 is false. Minus 45 is false. So it seems to work. All right. So is this an efficient algorithm? Well, to know that, we have to go through it line by line and see what's happening and if it's fast. So let's mark up the lines with their running times. This is constant time. This is also constant time. Might not even execute, so then it would be even faster. This is, you take the length of A, you divide it by 2, you assign it to M. That's all basic arithmetic, so it's constant time. Checking if X is less than A at M, that's array indexing and a comparison. That's constant time. This is constant time. This is constant time. Then there's this. How long does that take? So what is this doing? Yeah, so it's taking a slice of the list from position 0 up to the middle element. And then it's going to use that as an argument to recursively call binary search. Now, is that fast? Depends on the size of M, which is just half the size of the list, right? So actually, this takes O of n over 2 time. That's terrible, right? That means we're already looking through half the list just to do that. And then we're going to call it recursively. So O of n over 2, we actually we just write that as O of n as well, right? Because O of n means some constant times n that I don't feel like telling you, Well, just take that constant and divide it by 2. It's the same thing as O of n over 2. So here we have a problem. Slicing takes O of n time. So if we want this thing to be efficient, we'll have to restructure it next class in order to avoid slicing half the array like this, in order to do something that only takes constant time rather than copying half the array. So we'll leave it at there for today.